Hey everybody, welcome back to Quantitative Reasoning. Today we are finishing Chapter 11 with Section 11.7, and we're going to be looking at events involving and we will also work with conditional probability. So basically those are our two objectives. We will find the probability of one event and a second event occurring, and then we will talk about how to compute conditional probabilities. So let's just jump right into it. First, we need to talk about independent events. So two events are considered independent events if the occurrence of either one of them has no effect on the probability of the other. So a couple of examples of independent events would be flipping a coin. No matter how many times you flip a coin, what you get on one flip has no effect on what you get on the next flip. And another example of an independent event is rolling a die. It doesn't matter how many times you've rolled a 6, you still have the same chance of rolling any number on your next roll. So these are good examples of independent events. Now, if we know that two events A and B are independent, then we can find the probability of A and B by just multiplying the probability of A times the probability of B. Now, I don't want you to get this new formula confused with our old formula for OR events. So remember in section 11.6, we talked about how to find the probability of A or B. And this formula did involve the probability of A and B, but we've always been able to just look at the sample space and figure this out. With this formula, we are now able to calculate the probability of A and B by doing probability of A times probability of B. So notice the difference between the two formulas. So here is an example for us to look at together. So in example 1, a U.S. roulette wheel has 38 numbered slots. They are numbered 1 through 36, and then there's a 0 slot and a double 0 slot. 18 of the slots are black, 18 are red, and 2 are green. The ball can land on any slot with equal probability. And then in part A, they asked us, what is the probability of red occurring on 2 consecutive plays? Now, the trick to setting up these problems is to learn to restate the question with and. So if they're asking us the probability of red occurring on 2 consecutive plays, they're really asking us the probability that the first play gives us a red and the second play gives us a red. That's the only way to get red on 2 consecutive plays. Now, before we apply our formula, we need to think about whether these two events are independent. And the answer is yes, they are independent, because whether the first play comes up red or not, that has no effect on whether the second play comes up red. So now that we know that these two events are independent, we can apply our AND formula that we saw on the last slide. The probability that the first result is red and the second result is red is equal to the probability that the first result is red times the probability that the second result is red. So the word AND goes along with multiplication in our calculation here. All right, now, what is the probability that the first play comes up red? Well, they told us that there are 38 slots on the wheel, and they told us that 18 of them are red. So the probability that the first play comes up red would be 18 divided by 38. And then we've got this multiplication dot. And then we want to multiply by the probability that the second play is red. Well, on the second play, there are still 18 red slots, and there are still 38 total slots. So that probability is also 18 divided by 38. Now, to put this in your calculator, you can say 18 divided by 38 times 18 divided by 38. If you want it in fraction form, use your fraction key instead of your divide key. And that's what I'm going to do here. But read your instructions in MyLab, because sometimes they may ask for the probability in a fraction form, and sometimes they may ask for it in decimal form. On these examples, I will give you both the fraction and the decimal. But you know how to use the fraction to decimal button on your calculator, so you can convert between the two forms anytime you need to. So 18 divided by 38 times 18 divided by 38 gives us a simplified fraction of 81 over 361, and that is approximately equal to 0.224. And so now let's look at part B. What is the probability of green occurring on 2 consecutive plays? So if we think of this in terms of the word and, we're really looking for the probability that the first result is green and the second result is green. And the way to calculate this is to say the probability of the first result being green times the probability of the second result being green. Because again, these are independent events. Even if the first result comes up green, it won't affect whether the second result comes up green. So these are independent, and we can multiply like this. Okay, now, there are 2 green slots out of the 38 total slots. So the probability that the first result is green will be 2 divided by 38. And then we have this multiplication. And then the probability that the second result is green is also 2 divided by 38. So 2 over 38 times 2 over 38 will come up in fraction form as 1 over 361, and in decimal form, that is approximately 0.003. So now please don't take my word for this. I hope that you have your calculator in your hand and that you're actually punching in these numbers and seeing these results, and that you're practicing switching back and forth between the fraction and the decimal form. And then for part C, what is the probability of landing on an odd number on 2 consecutive plays? Okay, they did not tell us how many of the slots are odd numbered, but they did tell us that the numbered slots are numbered 1 through 36. So we can make a list of the odd numbers. The set of odd numbers on the roulette table then would be 1, 3, 5, 7, 9, all the way up to 35. So here are all of our odd numbers, and if we count them, 1, 2, 3, 4, 5, 6, 7, and so on, we have a total of 18 odd numbers here. Okay, now stating this question in terms of and, we need to find the probability that the first result is odd and the second result is odd. And we also need to ask ourselves if these are independent events. If I get an odd number on the first play, does that affect the probability of getting an odd number on the second play? And it does not. So we can go ahead with our formula. So because this is an and probability, we can say this is equal to the probability that the first result is odd times the probability that the second result is odd. Now from here, this is very similar to one of the previous parts that we did. For the probability that the first result is odd, there are 18 odd slots on the wheel, so that probability is going to be 18 divided by 38. And then times the probability that the second result is odd, and that will also be 18 divided by 38. And when you punch this in your calculator, your simplified fraction answer will be 81 divided by 361, and the decimal approximation will be approximately 0.224. So these are the same results we saw on the first part where we were asked to find the probability that we got a red, and that's not surprising because there were 18 red slots and there are 18 of these odd slots as well. So of course the probabilities are equal. Okay, now good news. The AND rule for independent events can be extended to cover any number of independent events that you need. So, for example, if we have 3 independent events, then the probability of A and B and C all occurring would be the probability of A times the probability of B times the probability of C. So as long as the events are connected by the word and, we can multiply the probabilities together. Okay, so here is example 2. And it says, assume that the probability of having a baby girl is 1/2. Part A, find the probability of a family having 3 girls in a row. Okay, so obviously these are independent events. Whether they have a girl the first time or not, that does not affect the probability of whether they will have a girl the second time. So let's state this problem in terms of and. The probability that the family will have 3 girls in a row is the probability that the first baby is a girl and the second baby is a girl and the third baby is a girl. So now with the word and in here, we see that we can multiply the probabilities together. So this is going to be the probability that the first baby is a girl times the probability that the second baby is a girl times the probability that the third baby is a girl. Now, for each baby, the probability that the baby is a girl is 1/2. So the probability that the first baby is a girl is 1/2, and that's going to be times the probability that the second baby is a girl, so times 1/2, times 1/2 for the third baby. And 1/2 times 1/2 times 1/2 is 1/8, or in decimal form that would be 0.125. Okay, now let's look at part B. Find the probability of a family having 4 boys in a row. Now this is a little different because they gave us the probability of having a girl, but now they're asking about a probability of having 4 boys in a row. So first, let's state this in terms of and. If they're going to have 4 boys in a row, then it means we're looking for the probability that the first child is a boy, and the second is a boy, and the third is a boy, and the fourth is a boy. So we've got these ands in here, and we know that that translates to multiplication. So if we state this in terms of our formula, it's going to be the probability that the first baby is a boy times the probability that the second is a boy times the probability that the third is a boy times the probability that the fourth is a boy. Okay, now we have to keep in mind that the probability they gave us is for a girl, but here we're trying to find the probability of having a boy. So every baby that's born is either girl or boy, and so that means that these two events are complementary. So the probability of having a boy is 1 minus the probability of having a girl. So the probability of having a boy is 1 minus 1/2, which is still 1/2, but we have to think about that. Like, we just can't take this number and plug it in, because if this number had been anything besides 1/2, then the probability of having a boy would not have been the same, you see. So now that we have this number, we can plug it in. So the probability of having 4 boys in a row is going to be 1/2 times 1/2 times 1/2 times 1/2. And that comes up 1/16, or in decimal form 0.0625. Okay, let's move on to example 3. And this one says, if the probability that South Florida will be hit by a hurricane in any single year is 5/19, then in part A, what is the probability that South Florida will be hit by a hurricane in 3 consecutive years? Okay, now for purposes of this problem, we can assume that whether they're hit with a hurricane in one particular year or not, that has no effect on whether they're hit with a hurricane in another year. So the events are independent, and we can use our multiplication rule. So let's state part A in terms of and. If we're looking for the probability that they'll be hit by a hurricane in 3 consecutive years, then we're looking for the probability that they'll be hit the first year and the second year and the third year. And since these are independent events, we can replace the ands with multiplication. So we'll be finding the probability that they're hit the first year times the probability that they're hit the second year times the probability that they're hit the third year. Now, they told us in the problem that the probability that they're hit in any one year is 5/19. So the probability that they're hit the first year is 5/19. And then that's times the same probability for the second year times the same probability for the third year. And when you put this in your calculator, you will get this horrible looking fraction, 125/6,859, or in decimal form, that's approximately 0.018. Now in part B, they asked us, what is the probability that South Florida will be hit by a hurricane in 4 consecutive years? So of course that would be the probability that they're hit the first year and the second year and the third year and the fourth year. So it would be this statement again, but just with a and the fourth year in there as well. So we know we're going to multiply, so it's going to be the probability that they're hit the first year times the probability that they're hit the second year times the third times the fourth. Okay, and for each one of these years, the probability that they will be hit is 5/19. So that would be 5/19 times itself times itself times itself, and that value comes out approximately 0.005. if we round off to 3 decimal places. Okay, in part C, the question changes a little bit. What is the probability that South Florida will not be hit by a hurricane in the next 4 years? So I want us first to state this in terms of and. Now, if they're not going to be hit by a hurricane in the next 4 years, it means they're not going to be hit the first year, and they're not going to be hit the second year, and they're not going to be hit the third year, and they're not going to be hit the fourth year. I know that in English we might naturally say they weren't hit the first year or the second or the third or the fourth. You see how I switched to or there, and it sounded very natural because we were talking about a not event. But when you're trying to figure out a probability, I want you to be careful about using and or. If you're trying to exclude all of these things from happening, it needs to be the word and. So I want to say I'm looking for the probability that they're not hit the first year, and they're not hit the second, and they're not hit the third, and they're not hit the fourth. That way I'm finding the probability that they're not hit in any of these years. Okay, so now we know that the and translates to multiplication, so it's going to be the probability that they're not hit the first year times the probability that they're not hit the second times the probability that they're not hit the third times the probability that they're not hit the fourth. Okay, now remember that in the problem they gave us the probability that they will be hit by a hurricane, and they said it was 5/19 for any one single year. Here we want to plug in the probability that they're not hit in a single year. So we can probably all agree that they're either hit by a hurricane or they're not hit by a hurricane. And so those two events are complementary. So the probability that they're hit is 5/19, but the probability that they're not hit is 1 minus 5/19, which is 14/19. So this is the value that we'll be plugging into our calculation here. The probability that they're not hit the first year is going to be 14/19, and then that's times the probability that they're not hit the second year, which is 14/19, times 14/19 for the third year, times 14/19 for the fourth year, and that gives us a decimal approximation of 0.295. Okay, now in part D, the question changes again. What is the probability that South Florida will be hit by a hurricane at least once in the next 4 years? Now, anytime they ask us to find the probability of something happening at least once, this can get to be a very complicated situation because there are a lot of different ways that at least once can happen. They could be hit the first year, or the second year, or the third or the fourth. Or they could be hit the first 2 years and not the next 2. Or they could be hit the second and third year but not the first and the fourth. Do you see how it can get really complicated really fast? So whenever you're asked to find a probability that involves at least once, we want to think of this as the complement of never. And this is surprising to a lot of students, but just think about it this way. They are either never hit in the next 4 years or they're hit one or more times in the next 4 years. So the probability that they are never hit plus the probability that they are hit at least once is 1. That means these two events are complements. And that means that the probability that they're hit at least once in the next 4 years is 1 minus the probability that they are never hit in the next 4 years. And we calculated this probability on the previous slide in part C. So if you remember, this value was 0.295, and so we're going to calculate 1 minus 0.295, and that is going to be 0.705. You might have to think about this a little bit for it to sink in, because a lot of students expect that the complement of never being hit by the hurricane is that they're hit every year by the hurricane. But those are not complements because there are other things that can happen. Remember, complements cover every possibility in the sample space. So these two events are complements. Either they are never hit by a hurricane or they are hit at least once, meaning once, twice, 3 times, 4 times, however many. every event is covered either here or here, you see. Okay, let's go on now and talk about dependent events. So two events are considered dependent events if the occurrence of one of them has an effect on the probability of the other. So here are some examples of dependent events. Drawing a card from a deck without replacement is a dependent event because whatever card I draw from the deck the first time, if I don't put it back, that changes the probability of drawing a particular card on the next draw. Drawing names out of a hat is a dependent event because if I draw someone's name out of a hat and I don't put it back, then that changes the probability for the next name that I draw out of the hat. So when we calculate probabilities for dependent events, this is how we do it. If A and B are dependent events, then the probability of A and B is equal to the probability of A times the probability of B given that A has occurred. So when we do the probability of the second event, we assume that the first one already happened. Now we don't want to be stuck writing the words given that and occurred. So here is a shorter way to write this. We'll still have probability of A, and we'll still have the multiplication dot. But instead of writing the words given that, we will use a vertical line. So it will look like this. Probability of B given that, see that vertical line represents the words given that, A has occurred. So A comes next. So the way we read this is the probability of B given that A has occurred. And that will save us a little writing. Okay, so here is example 4. Let's look at this problem. It says you have won a free trip to Madrid and can take 2 people with you, all expenses paid. But bad news. 10 of your cousins have appeared out of nowhere and are begging you to take them. You write each cousin's name on a card, place the cards in a hat, and select one name. Then you select a second name without replacing the first card. If 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins. So you can probably look at this and tell that these are dependent events, because if we start with 10 names in the hat and we draw one out, then the next time we draw a name, there are only 9 names in the hat. So right away, the probability has changed from the first drawing. And so we need to use our formula for the probability of dependent events. So we will write the probability of drawing the names of 2 Spanish speakers is equal to the probability that the first name is a Spanish speaker times the probability that the second name is a Spanish speaker, given that the first one was a Spanish speaker. So remember, we use this vertical line to stand for the words given that. So all that really changes for our formula is that when we write down the second probability, we have to do it assuming that the first event took place. Okay, now there are 10 names in the hat and 3 of the cousins speak Spanish. So the probability of drawing a Spanish speaker on the first draw would be 3/10. And that's going to be times the probability that the second one speaks Spanish given that the first one did. Now, pulling a name out of the hat means that there are now only 9 cards left in the hat. But assuming that the first one was a Spanish speaker, there are now names of only 2 Spanish speakers left in the hat. So the probability that the second name will be a Spanish speaker is just 2 divided by 9. Okay, now you can enter this in your calculator. In fraction form, you would get 1/15, but in decimal form, this would be approximately 0.07. And let's look at example 5. You are dealt 2 cards from a 52-card deck without replacement, so that means we're dealing with dependent events. Find the probability of getting 2 kings. So the probability of drawing a king on the first draw and then drawing a king on the second draw is going to be the probability that the first card is a king times the probability that the second card is a king, given that the first one was a king. Okay, now there are 4 cards in the deck that are kings, and there are 52 total cards, we know. So the probability of getting a king on the first draw would be 4 divided by 52. Now for the second card, we want to find the probability of getting another king, assuming that we already drew out a king. So if we drew one, then now we're down to 3 kings and 51 total cards. So now we're going to multiply by 3 divided by 51. And this would give us a decimal approximation of 0.005. And here is example 6. 3 people are randomly selected, 1 person at a time, from 5 freshmen, 2 sophomores, and 4 juniors. Find the probability that the first 2 people selected are freshmen and the third is a junior. Now, if we're going to be calculating probabilities, we're going to need to know how many people are in our sample space. So let's go ahead and add that up first. The number of people in our sample space is going to be 5 plus 2 plus 4. So that's a total of 11 people in the sample space. Now they said find the probability that the first 2 people selected are freshmen and the third is a junior. So to state that using the word and, they want us to find the probability that the first person is a freshman and the second person is a freshman and the third person is a junior. And we know that the and translates to multiplication, but the probability of these last 2 events will change from what it was in the beginning depending on what happens with the first event. So we'll have to keep that in mind when we come up with the probabilities for these second 2 events. So we're going to be finding the probability that the first person is a freshman times the probability that the second person is a freshman given that the first one was, times the probability that the third one is a junior given that the first 2 were freshmen. Okay, now for the first probability, out of 11 people, 5 of them were freshmen. So this first probability is 5 divided by 11. For the second probability, we want to find the probability that the second person is a freshman, assuming that the first person was. So now we're down from 11 people down to 10, and one of our freshmen has already been selected, so we're down to 4 freshmen. So the second probability will be 4 divided by 10. For the third probability, we're now down to 9 people, but 4 of them are juniors. So the third probability is 4 divided by 9. And entering this into the calculator, we will get a decimal approximation of about 0.081. Okay, now in example 7, we're going to do some card examples. So part A says you are dealt 3 cards from a 52 card deck without replacement. So these are dependent events. Find the probability of getting 3 hearts. So I'm going to write it like this with just a capital H to stand for hearts. So the probability of drawing 3 hearts would be we draw a heart on the first draw and a heart on the second draw and a heart on the third draw. And remember, these are dependent, so as we go along, we'll need to assume that the previous card was a heart. So it'll look like this. We want to do the probability that the first card is a heart times the probability that the second card is a heart, given that the first one was a heart, times the probability that the third one is a heart, given that the first 2 were hearts. Now, we know there are 13 hearts in the deck of 52 cards. So the probability that the first card is a heart is going to be 13 divided by 52. Now, that's going to be times the probability that the second card is a heart, assuming that the first one was a heart. So if we've drawn a heart from our deck, now we're down to 12 hearts and 51 total cards. So the next probability will be 12 divided by 51. And then for the third probability, we want to find the probability of getting a third heart, assuming that the first 2 cards were hearts. So now we're down to 11 total hearts and 50 total cards. So the third probability will be 11 divided by 50. And when you multiply this on your calculator, you'll get a decimal approximation of about 0.013. Now for part B, you are dealt 4 cards from a 52 card deck without replacement. Find the probability of getting 4 face cards. If you would like to pause the video and try this one on your own, then go ahead and do that. And now I'll go through it with you. So on this one, I'm going to leave out some of the notation we've been using because that can really slow us down sometimes. We'll just say that the probability of drawing 4 face cards without replacement is going to be the probability that the first card is a face card times the probability that the second one is a face card. But remember, we have to assume that the first one was. And then times the probability that the third card is a face card, and so on. Each time assuming that the previous cards were face cards. So there are 12 face cards in this deck of 52. So the probability that the first card is a face card is going to be 12 divided by 52. Now that's going to be times the probability that the second card is a face card, assuming that the first card was. And so if we drew a face card the first time, now we're down to 11 face cards and 51 total cards left in the deck. So that would be a probability of 11 divided by 51. And then for the third card, we assume that the first 2 were face cards. So now we're down to 10 face cards and 50 total cards in the deck. And then for the fourth card, we assume that the first 3 were face cards. So now we're down to 9 face cards and 49 cards in the deck. So when you multiply these 4 numbers together, 12 divided by 52 times 11 divided by 51, and so on, then you'll get a decimal approximation of about 0.002. Okay, now we're going to shift gears a little bit and look at conditional probabilities. So we have already seen that for 2 dependent events, A and B, the probability of A and B is equal to the probability of A times the probability of B, given that A occurs. And we've been using that shortcut notation that I showed you. So here it is officially. The probability of B, given that A occurs, is called a conditional probability because we're finding the probability of B under the condition that A occurs. That's why they call it a conditional probability. And we write this probability as the probability of B vertical line A. And we've been doing that already. Now you might be thinking that in order to calculate this value, the probability of B given that A occurs, that we might have to rearrange our formula. But actually, instead of doing that, what we'll do is we'll think of the conditional probability, the probability of B given that A has occurred, as the probability that event B occurs if the sample space is restricted to the outcomes associated with event A. So whatever would happen to the sample space, assuming that A has already occurred, that's the sample space we will use to find the probability of event B. It is much easier than it probably sounded on the last slide. So let's look at an example. A letter is randomly selected from the letters of the English alphabet. Part A. Find the probability of selecting a vowel given that the outcome is a letter that precedes H. So let's write down what we're trying to find in our probability of B given A notation, okay? We're trying to find the probability of selecting a vowel given that the outcome is a letter that precedes H. So that's going to be the probability of finding a vowel given that the letter precedes H. See, the fact that we already know the letter has to precede H changes our sample space from all 26 letters of the alphabet to just the ones that come before H. So let's write those down. Our sample space is now the set containing A, B, C, D, E, F, G. These are all the letters that precede H. So we're going to find the probability of selecting a vowel given that we already know this other part. So how many vowels are there in this limited sample space? Just these 2, right? The A and the E. So the probability of getting a vowel, assuming that the letter precedes H, is just 2 divided by 7, or if you want a decimal approximation, it would be approximately 0.29. In part B, it says find the probability of selecting a consonant given that the letter precedes K. So how would we write this down in our B given that A notation? We would say the probability of selecting a consonant, and you can abbreviate, given that the letter precedes K. That's the probability that we're going to find. So the sample space is limited to this part that comes after the vertical bar. So let's write down the sample space of letters that come before K. So the sample space would be A, B, C, D, E, F, G, H, I, J, and it would stop there. Okay, that's a total of 10 letters, right? And how many of them are consonants? Let's see. 1, 2, 3, 4, 5, 6, 7. So there are 7 consonants. So the probability of selecting a consonant, given that we know the letter comes before K, would be 7 divided by 10 total letters. So that's a fraction of 7/10, or a decimal value of 0.7. Okay, example 9, back to the deck of cards. Find the probability of getting a heart given that the card you were dealt is a red card. So to write this in our conditional probability notation, we could write the probability of getting a heart given that the card is known to be red. Okay, now we know that there are 13 hearts and 13 diamonds, and those are all the red cards. So there are 26 red cards in the deck. 13 of them are hearts. And so the probability of getting a heart, given that the card is red, is going to be 13 over 26. And that's going to simplify to 1/2, or in decimal form 0.5. But what I want to make sure that you understand is that whatever comes after the vertical bar limits our sample space. So instead of the sample space being the whole 52 card deck, we are limited to just the red cards. Now for part B, find the probability of getting a king given that the card you were dealt is a face card. So we would write that we're looking for the probability of getting a king given that we know we're getting a face card. And so there are 12 face cards in the whole deck, and within the face cards we know that there are only 4 kings. So the probability of drawing a king, knowing that we're going to get a face card, is going to be 4 divided by 12, and that's going to simplify to 1/3, or a decimal approximation of 0.33. And part C, find the probability of getting a spade given that the card you were dealt is a black card. And so the probability of getting a spade, given that we know we're getting a black card, is going to be written this way. The probability of getting a spade, given that the card we're drawing is black, and we know that there are 26 black cards in the deck, and 13 of them are spades, and so the probability of getting a spade, given that we know we're drawing a black card, is going to be 13 out of 26. And of course that again is going to simplify to 1/2, or 0.5. And part D, find the probability of getting a red card given that the card you were dealt is a heart. Okay, now see, this is why it's so important to write the problem down, because this is not the same problem as we had a while ago when we were supposed to be finding the probability of getting a heart given that we're drawing a red card. This time we're supposed to be finding the probability of getting a red given that the card we're drawing is a heart. So we would write that down as the probability of getting a red given that the card we're drawing is a heart. Now our sample space is limited to the hearts, and we know that there are 13 hearts in the deck. Here they are right here. So that is our sample space. And within these 13 hearts, all 13 of them are red. And so now when we try to find the probability of drawing a red card, knowing that we're drawing a heart, there are 13 red cards within the heart sample space. So the top number is 13. And then the sample space is just all the hearts, so that is also 13. And 13 divided by 13 reduces to 1. So we know that a 1 represents a certain or a guaranteed event. And I think this will make sense to you if you think about it this way. If you know that you're drawing a heart, you automatically know that card is red, right? So the probability of getting a red, if you already know the card is a heart, that probability is 100%. It's guaranteed the card is red if it's a heart. All the hearts are red. So it makes sense that this probability would be 1. Okay, now let's do the same kind of problem, but this time with one of these real-world tables that we've been seeing in some previous problems. So example 10 says, assuming that these numbers are representative of all U.S. women ages 40 to 49, find the probability that a woman in this age range, part A, has a positive mammogram given that she does not have breast cancer. Okay, now remember, whatever comes after the given limits our sample space. So here, it is given that she does not have breast cancer. So the only part of the table we want to look at is the part that talks about the women that are known to not have breast cancer. Okay, so now we want to find the probability that a woman in this group has a positive mammogram. So to write it in our conditional probability notation, we would say the probability of having a positive mammogram given that there's no cancer is going to be the number of women who had a positive mammogram from this group, which is just 6,944, divided by the total of those who had no cancer. And the bottom row is the total, so that would be 99,200. When we get a decimal approximation for this, 6,944 divided by 99,200 just happens to come out as a terminating decimal, and it comes out to 0.07. And let's look at part B together. So we want to find the probability that a woman in this age range does not have breast cancer given that she has a positive mammogram. Okay, so given that she has a positive mammogram, we want to limit our sample space to those who had a positive mammogram. So that would be this top row. And so the probability that a woman does not have breast cancer, given that she has a positive mammogram, would be this 6,944 divided by this total, which is 7,664. See, that's the total of just the women who had a positive mammogram. And this decimal approximation is about 0.91. So let's think about what this says here. We just found, according to this table, for these women, the probability that a woman did not have cancer, even though she had a positive mammogram, was 0.91, 91%. So look at this. Out of the women with a positive mammogram, 9 out of 10 of the women who had a positive mammogram actually ended up not having cancer. Isn't that surprising? But I think what's happening here is that the mammogram just can detect abnormalities in the tissue. It can't always tell you if it's cancerous. You have to go do more testing. So most of the time, for these women anyway, even when the mammogram said there was something there, further testing actually found out that it wasn't really cancer. So that's good news, right? And here's part C. Find the probability that a woman in this age range has breast cancer, given that she has a positive mammogram. And so again, we want to limit ourselves to just those with a positive mammogram. And the probability that she has breast cancer, given that she has a positive mammogram, would be this 720 divided by this 7,664 for a decimal approximation of about 0.09. And finally, part D, find the probability that a woman in this age range has a positive mammogram given that she has breast cancer. Okay, so this time, the given part is that she has breast cancer, so we are limiting ourselves to just this part of the table. So the probability that she has a positive mammogram, given that she has breast cancer, would be this 720 divided by this total with breast cancer of 800, and that works out to exactly 0.9. Okay, you guys, we have made it through one more section, and we have made it to the end of Chapter 11. I know that dependent events and conditional probability can be a little scary sometimes because we don't often think in these terms, but I think you can do it with a little practice. And as always, if you get stuck on anything and you need help, just reach out to your instructor and we will be glad to help you. All right, good luck, and I'll see you in the next video. Bye-bye.